Hello, welcome back to our chemistry instruction. Dr. Bettina Heinz is with you again today. And on the menu we have measurements. So measurements are so important for science because we have to collect data all the time. So this category is divided into two parts. We will begin with part 1, and this is what's on the menu. Exactly. So we are talking about obtaining data. Then when we obtain data, we have to be very careful in regarding significant figures and the rules for calculation with these obtained significant data points. Addition, subtraction, multiplication, division are a little bit separate in their rules. Degree of error related to standard deviation of measurements, of a collection of measurements, scientific notation, rounding rules, and the SI system or Système International for units and measures, which is of course almost the same as the metric system, and then what the meaning of dimensions is. And a dimension is a combination of a figure and label or a numerical coefficient or factor or figure, number, and a unit together. So in chemistry as well as in other sciences, we deal with dimensions. So numbers alone are not enough. We always have to know what's behind it, what type of unit is involved, what kind of unit is attached to the number. And I will demonstrate a little bit here on the Elmo, on the projection screen, some different types of measurements as far as difference in accuracy and precision goes. Now, accuracy means what is the real value of what I'm looking for. If I look at this orange square or a rectangle here, this object knows practically its area. It knows how long it is on each side. So the length and the width are known to the material, but the material won't tell me. So the actual value is what we refer to as related to an accurate measurement. So accurate means we are close to the actual value. Now I have different means of obtaining the actual value depending on what type of tools I use. So we are only as good as the tools we use. Now I can use a foot to measure off the side lengths of this rectangular area. And that's not very accurate or precise. However, we get sort of an idea, but it's not good enough for scientific research or considerations. So the foot is very good. The foot has been standardized, of course, in our world. It's exactly 12 inches, as we know. But originally, the real foot was used, or the hand span, or the arm length. So earlier, different types of measurements were used, and they were good enough to measure off fabric or some other pieces of wood or things like that. But for science, we have to be a little bit more accurate and precise. I'll tell you the difference in a minute, what is understood by accurate tools and precise tools. Ideal is that they are both. Now here I have a type of ruler that has the numbers here assigned to various subdivisions, and each one is subdivided by some more subdivisions, which we call increments. Now if I measure the side length of this rectangular space, then I would estimate, or I could pretty well say it's 3.5 at least, and then I have to sort of do some guesswork. So it's 3.9 I would estimate. So the last digit 3.9, that means the digit in the tenths is uncertain. It's a little bit guesswork or estimation work. It's pretty close to the true value, but I'm guessing. There's some fluctuation in this measurement. So we can say 3.9 plus minus 0.1. This is called the degree of error. Now if I take a better tool, like this one, which has more increments, meaning more subdivisions, I can get what we call more significance in my reading, meaning I will get more significant figures for my measurement. So if I read the same side length off with this measuring device, with this ruler, and we don't have any particular units, we'll just say units in general. So we have here 3.9. I can definitely say with certainty it's 3.9. And then the hundredths region is now a little guesswork. So I have to estimate the number behind the 9. And I can do that sort of in good faith and say it's 3.9. Well, it's not quite in the middle, so it's probably 3.92 or something like that. So the last digit is uncertain, but I can still use it as a significant reading. So in the measurement tape up top, I had 3.9, so 2 significant figures. In the bottom, I have 3 significant figures because I had 3.92. Now, if I measure the other side of the rectangle, we have the same problem here. So you see I have 2 point something. So it's probably a little over 2.3 plus minus 1. So the true value is someplace between 2.2 and 2.4. That shows you the range of error or range of certainty, the last possible certainty. Everything else is pure guesswork. So again, we have 2 significant figures here, but if I use the other more precise measuring tool, I can say, it's 2.3, and then it's somewhere between 3 and 4, definitely. So I can sort of estimate the last digit in the hundredths, and that would be 2.38 plus minus 0.01. So the true value is somewhere between 2.37 and 2.39. So you see, I have more significance in my measurement. I can get more digits. And that is what we try to achieve in scientific work. So I hope that explains things very well. What if I want to calculate the area of the space? Then it would be length times width, or A times B. And I'm going to turn this over because I did some calculations already. See, here I measured last night the number of units. And if I want to calculate the area with a bad measurement, then I get the calculation 3.9 times 2.3, and that gives me 8.97 in my calculator. And now that would be 3 significant figures, which is not good. I cannot use them because that would be lying. I did not have that good measurements to warrant 3 significant figures, because the multiplication rules and division rules of working with significant figures is that the weakest link makes the strength of a chain. That means the answer cannot have more significance than the individual measurements. So you have to tailor it down to the number that had the lowest amount of significant figures. And I have to do that here, sorry. So it's 9.0. Now, for many people who are used to doing good math, they can't understand this, and it hurts to drop some valuable numbers. But as far as measurements goes, we just have to stick to the rules. Now, if I use a better measurement tool, I had 3.93 times 2.36. So 3 significant figures, 3 significant figures. The calculator gave me 5, but remember, I can't use those. I have to round to the lowest amount of sig figs, as we say for short. So both were 3, so this has to be tailored down to 9.27. That means the other units just have to drop. Sorry about that. So you see the reason now for having good tools, depending on what type of information you want to study and work out. So let's look at the first illustration page here. Now zoom in a little bit so you can see it better. Yes. Now, many people get accuracy and precision a little bit mixed up. But I already told you, accuracy is easy to remember. That's how I remember it. Accuracy and actual somehow starts with the same two letters. So we can say accuracy means how close are we to the real system immanent or actual value. Precise or precision means how repeatable are my measurements in giving me accurate results. So if the repeated measures or measurements turn up to give me consistent measurements or consistent dimensions or values, then I can say my tool is precise. Now, the more precise measuring tool will, of course, offer me reliable, repeated measurements. So things don't fluctuate so much. A bad tool will have a large degree of standard deviation. A precise tool will more or less give me pure accurate values. So little swaying off the actual value. Now, people often illustrate this concept with a dart game. And let's look at this. Here are all the dots on the outer rim of the bullseye dart table. And the dots are all out, on the outer rim, but they're very close together. So the person was pretty precise in his or her throwing of the dice, but never reached the bullseye. So that means it was very inaccurate, but precise. Here we have in the middle, we have a scattering of all the different positions, which of course means this person has to practice a little bit more. So it's unprecise and also inaccurate. But if we look at here on the right, we can see, aha, this person really knows his or her game. So they are very precise and also accurate in their throws. If we look at this with some little curves, we can say the number of measurements, which is this axis here, the y-axis or ordinate. And if we look at this axis, we can have the distribution curve of a certain number of measurements. The more the better for statistical purposes. Now we see here, if the red point means the actual value, that this device is pretty much off, although the data points are in close range. That means not much deviation. However, always in the wrong part of the field, so to speak. So this would be, for instance, observed for a measuring tool that has a systemic error, a built-in error. So it's still a precise tool, but it just has to be realigned or re-standardized. Like this lady here on the scale is hoping that this scale has a systemic error, that she's not really 160 pounds, that she's actually 120, if that helps any bit. So here we have a wide spread of data points. So here we see this measuring device is pretty much off the mark and also very scattered, so not very precise tool. Throw it out. Might not be able to be fixed. Now this one is perfect. You see it has a nice narrow range of data points, low standard deviation, and it is right on the mark, so the most of the measurements are close to the accurate value. A little spread, that means a perfect precision is not possible. That would be just a line directly on the mark. Now we talked about units, and it's important to consider that we deal with a certain internationally accepted system, and that is called the System International, or in French it would be the Système International. And that's where the SI comes from, the International System of Units and Measures. So it was not that long ago, really. So in 1960, the General Conference of Weights and Measures met and decided to make a universal system of units. and in 1964 it was adopted by the National Bureau of Standards. Now, interesting, there are 7 quantities that are of importance for chemistry and that are attributed with certain units that are considered the standards. So every other unit is considered a derivation of one of these 7 SI units. Now, what can we measure in science? We can measure mass, length, time, electric current, temperature, luminosity, and the quantity of a substance. The mass is standardized by the kilogram, and all these physical standards are exhibited in the Museum of Sèvres, which is close to Paris, as the original kilogram, original meter. Today the meter is digitally, photo with the help of radiation, wavelength determinations. It is standardized today, but in the old days it's still the original meter stick preserved in the museum of that historical building. Now, time is actually not belonging strictly to the metric system. That means the unit based on tens. It is a unit based on the number 6. So it's the second is still the standard. And the electric current is the ampere. I overlooked the length. Yeah, we talked about the meter. Yes, I'm sorry, we did. The electric current is the ampere. Temperature is measured in Kelvin. Luminosity is candle power, candle strength. So candela, CD, is the unit. And the quantity of the substance is the mole. The unit itself is MOL, but the description of the unit is the mole with an E. So we have a lot of derived units. The gram is, for instance, 1,000th still of a kilogram. A kilometer is 1,000 meters. Degree centigrade is Kelvin minus 273. Cubic centimeter is centimeter times centimeter times centimeter. So volume can be derived from the length units, so the cubic length units. The joule or the joule is Newton times meter. And the Newton, a unit for force, is derived. And you see you can all base the units and describe them with the help of these 7 original units. So kilogram times meter over second square is, you see, all 3 SI units, standard units, the basic 7. 3 of the basic 7 are in the Newton. So you see every unit can be derived from original units. Some phased out units, but still common, is the calorie. The joule is 4.18, or let's say 1 calorie is 4.18 joules, roughly speaking. Metric system means that all the units are based on powers of 10. Scientific notation is a way to describe a measurement in a very straightforward way, a very standardized way. That means we write any measurement in a 2-part setup. We have a numerical coefficient, which should be one number, and then a decimal point and whatever significant figures we still have along with it, and then a power of 10. So for instance, 100 grams, which is 1 kilogram, would be 10 times 10 times 10 grams, or 1 times 10 to the cube grams. Now, if we have 1200 millimeter, for instance, let's say we measured 1200 millimeters, then how do I know whether the zeros are significant or not? Well, the scientific notation will get us out of the ambiguous situation. If the zeros are part of the measurement, I can put them into the coefficient of the power number. For instance, 1.200 have to be included then, times 10 to the third power. And we see here 4 significant figures. Now, if the zeros were just placeholders, just important to show that the 12, the 1 and 2 are in the thousand stills and thousand and hundreds region, then I would not include them up front here because they're not part of the measurement. So it's 1.2 times 10 to the third power of millimeters. So you see how we can bypass this ambiguous situation. So scientific notation means that any number has to be converted into this format, a number with a decimal and any digits that follow it times a power of 10 number. Negative, small numbers will have negative powers, and large numbers will have positive powers. Now you see here, these zeros are just placeholders, and these zeros here in the middle are part of the measurement, so they have to be included. So here we have it again, and you can see here in the bottom part the different powers of 10. They all have names, of course, like centi, deci, mega, milli, pico, micro, kilo, etc. Now, what if you have a measurement that has to be rounded? So we have to remember, when we have to use significant figures, we have to round according to the rules. In this case, we have an odd-even rule. And this is very interesting because normally we always rounded any 5, any so-called naked 5, to the next higher digit. In science, we want to be fair. So we have the rule that if the previous number becomes even, we round a naked 5. That means a 5 that has nothing behind it, just 0, so to speak. And if the number becomes odd, then we just drop the 5. However, a 5 that has numbers behind it will always be rounded. But a naked 5, we have the odd and even rule. So a 5 that is rounded to the next or the previous even number is going to move. And if the previous number does not become even, then it's just plain old dropped. So here we have an example, for instance, 1.5000. Let's say we have to round it, and the previous number becomes even. Then we will round it. Here we have 2.5, and here the number, when we round the 5, the naked 5, will become 3. So 3 is an odd number, so we can't do the process, so we have to just eliminate the 5. Here are some examples for rounding. Let's round to the nearest tenths. So what does that mean? Here we have a number, nearest tenth. So that means that's this digit right behind the decimal. So this becomes 3.4. Here, the 5 is dropped. So it's also 3.4. What about this number, 3.4492? Here, of course, everything behind the 4 is less than 5, so it will be dropped. Here, we don't have a naked 5 because it's followed by a digit like 1, not 0. So it has to be rounded. No, excuse me, then we leave the 5, 3.5, so everything else will be dropped. So here are again the digit positions. Like here's the decimal, we have the ones, the tens, the hundreds, and so on. And everything on the right side of the decimal is a fraction. So we have the tenths, the hundredths, and the thousand stills, etc., etc. So 100 times, 10 times, 1.1 or 1/10, 100ths, 1,000ths. We will come soon to the measurement 2 part. Here we will show a lot of equipment. But before we move on, let me tell you something about how we apply the dimensional analysis method in calculations. Dimensional analysis is very helpful for the chemist and for the student of chemistry. Remember, math is no problem if you stick to the rules and be straightforward and consistent and keep the faith. So it's a very direct and consistent method. Calculating with numbers and units is a little different from calculating just with plain old numbers like you would do in math. Here we have a lot of conversions of units. We have to deal with ratios and measurements, etc. So remember, a dimension is, again, factor, label, as some say, or number and unit. Together we call that a dimension. So if we want to do a little calculation and say, ask us, how many inches are 2.8 feet? Now these are not SI units, but we are very comfortable with these units and they are our good old friends and we like to still use them. But if we have to do a scientific paper, then we cannot use them. Then we have to stick to the SI units. So 2.8 feet I measured. So we see two sig figs, or two significant figures. Here we have our unit ratio. So 12 inches and 1 feet. Now you might ask, 12 inches, that's two sig figs, right? No. Ratios are exact numbers. So they do not follow the rule of significance because they are fixed exact number. So we don't mess with these numbers. So they don't have to be incorporated in our significant figure calculation. So 2.8 times 12 is 33.6 inches. Now in order to adhere to the rules of significance, remember, we have to tailor down the answer, even though our little calculator gave us more, to 2 sig figs. And therefore I have to round the 6. So it's 34 inches. Thank you very much for listening and watching. See you next time.